Well, hello everyone, this is Chris Bear back again with The Ancient Scholar. And today I'm going to be talking about more gas laws. More specifically, I'm going to be talking about Graham's Law. And probably what I'm going to do is I'm going to make a couple of different videos, maybe even a few videos on Graham's Law. The concepts can get a little complicated, a little complex with Graham's Law, and I'm going to want to take some time to explain them. And there is a significant amount of math involved. It's certainly not, calculus, analytical geometry, anything like that. But there's certainly the concepts are a little more difficult than some of the concepts that we've covered thus far. So what I'm going to do today is I'm really going to talk about Graham's Law qualitatively, so we can develop the intuition. And really, that's the most important part, is that we develop an intuition for what's going on, and then the math can come later. In fact, I would suspect that a lot of the allied health respiratory science programs probably aren't going to spend a significant amount of time making you calculate some of the concepts of Graham's Law, but rather want you to know the concepts, conceptually understand what is going on. So what is Graham's Law? Well, at its core, at its foundation, Graham's Law is diffusion. And specifically, we're talking about diffusion of gas molecules. So that really is what Graham's Law is diffusion, rates of diffusion. How quickly does a certain gas molecule diffuse? Now, before I go any further, let's just go ahead and cover, or just go ahead and refresh ourselves on what the concept of diffusion is. So, if you can imagine that I have a container, and I have, we'll just say, some gas homogeneously mixed in this container. Maybe it's nitrogen, maybe it's helium, maybe it's hydrogen, whatever kind of gas. And it has a certain pressure and a certain density and volume and so on and so forth. We don't need to really talk about that right now. I have a gas dissolved in this container, and then I add another gas up here. Now what's going to happen is that gas is going to move, these molecules are going to move from this area of high concentration where I initially added it, it'll move from the area of high concentration, and these molecules will distribute themselves out equally, or they'll try to distribute themselves out equally within this container, and they'll try to be homogeneously mixed in that container, if you will. That is what diffusion is. It's the movement of molecules, particles, dissolved stuff, if you're talking about fluids, or liquids, I'm sorry. In this case, we're talking about gas. It's the movement of gas molecules from area of high concentration to area of low concentration. And we know, or we will know, that not all gas molecules diffuse at the same rate. Some are going to diffuse quickly, some are going to diffuse more slowly, and that's what Graham's Law gets into, is it asks these questions, or helps answer these questions. How does gas diffuse? And gas can diffuse through several different what we call mediums. In this case here, I had a gas diffusing through a gas. We can also have a gas diffuse through a liquid. And we can have a gas diffuse through a membrane. This is important because we have all three of these concepts occurring. I have gas diffusing through a gas when we talk about the alveoli and our airway. We have gas diffusing through gas, carbon dioxide, oxygen. We have gas diffusing through a liquid when we talk about our circulatory system, because we do have a certain pressure of gas within our blood at certain points in our body. Obviously the pressures change depending on where in the body we're looking at, but there is gas diffusing through our blood in gaseous form. And we also have gas that has to cross or diffuse through membranes. And specifically what we talk about a lot in respiratory care is gas diffusing through what's known as the alveolar capillary membrane. The gas has to get from inside of the alveoli through the membrane into the circulatory system. And if we're talking about oxygen, some will be dissolved in the blood, and most of it will actually be transported in the form of oxyhemoglobin or attached to hemoglobin molecules in red blood cells. So clearly, all three of these things will occur in our body. Okay, so hopefully we have a little better understanding, a little better idea of what diffusion is, specifically diffusion of gas molecules. Now, let's just go back to that container analogy, or you know what, let's go back to a room here. I have a little house, I have a room inside of that house, and maybe I'm standing here. And go back to our high school days, and I remember high school people, maybe a little earlier than that, people would have these little things called stink bombs, and they would basically release a real pungent odor that kind of smelled like rotten eggs. And I remember one time being on a bus and somebody had lit a stink bomb on the bus, and the bus filled up with this rotten egg stench, and everybody thought it was really funny. Obviously, I probably wouldn't think that it was very funny at this point in my life, but I think it was funny at the time. Well, let me just go ahead and give you guys a fact. We know that at standard conditions, so standard atmosphere, nitrogen, and nitrogen makes up about 80% of the atmosphere, and nitrogen molecules move at about 1,100 miles per hour. A little faster than that actually. But I have nitrogen molecules moving at 1,100 miles per hour. That is quick. That gas in our atmosphere under standard conditions moving at 1,100 miles per hour, that is quick. So we can assume that if there are other gas molecules out and about, they're probably moving fairly quickly as well. We can assume that, and we'd actually be right. So I drop a stink bomb, and it starts releasing that pungent odor, and if those molecules are traveling at 1,100 miles an hour, would, at least logically, I would think that it would take the amount of time that it would take to get from where it got dropped in the room to where I began to smell it would be a minuscule amount of time. 1,100 miles an hour, I mean, that's almost twice the speed of a commercial jet. So these should get to me almost instantaneously, I should smell. But what do we know happens? It's not instantaneous. It takes some time for those molecules to get to us, for those molecules to diffuse to us. So we got to think, what is going on? If they're traveling at a, I don't know what they're traveling at, but if the nitrogen is traveling around 1,100 miles per hour, certainly these guys have got to be going really quick. What is going on? And therein is kind of the crux of what's going on. That in our day-to-day life, we don't experience it because we can't see it. But we are bathed in an ocean of gas molecules. We can't see the gas molecules, and the light, the visible spectrum of light that comes to our eyes, that our eyes can see, that light doesn't really interact with the electrons and the gas molecules in the atmosphere, right? So we don't really see it. The molecules in our atmosphere are invisible, for the most part, invisible to the visible light that we see. So we can't detect this, but we are literally bathed in billions and billions and billions and billions and billions and billions and billions of molecules. We're bathed in them everywhere. And hopefully that starts making some intuition that if I have a container even though these molecules are very quick, if I have billions and billions and billions of these molecules, and I introduce a molecule of another gas in that container, yeah, that molecule is going to be moving around very quickly, but what's going to happen is that molecule is going to collide with another molecule, and collide with another molecule, collide with another molecule, collide with another molecule. Maybe I'm down here, and it is just going to randomly collide and collide and collide at, 1100 miles an hour or whatever, and continue colliding, and then finally, maybe eventually it'll work its way to me. And that's what we call a random walk, and that is the basis behind something known as Brownian motion, kind of the random movement of molecules. And you can see this on a microscope. When you look at a microscope, and you can see little dissolved particles, and they're just kind of wiggling around and randomly going here and there, and they're actually being bombarded by other molecules. So that's what's going on, and it's this random walk of smashing into other molecules and here and there and everywhere, which actually prevents this diffusion from being more or less an instantaneous process. So hopefully that makes sense. Hopefully there's some intuition of what's going on with diffusion. Now in the next couple of videos we'll start quantitatively discussing diffusion, making more quantitative sense of it, and talking about which molecules are going to diffuse faster under which conditions, because it's really interesting when you talk about carbon dioxide and oxygen and how they diffuse. Okay guys, thanks for hanging in there.